All right, let's go ahead and get started. So this chapter of our book is called Analytic Trigonometry, chapter 7. I've kind of combined that with the graphing in chapter 5 because to me, graphing trigonometry is really kind of analytic in my mind. The book obviously disagrees with me, but I don't care because this is my class, so we do what I want. All right. So today what we're going to be talking about is 7.1 trigonometric identities. All right. And so I'd like to define an identity because it's a good thing to know. And you may not know what it is. So an identity is an equation, but it's kind of a special equation. It's an equation that is true no matter the value of x. And when I say x, I really mean the value of the variable, whatever the variable is. But we usually use x, so I'll go ahead and just say that. So most of the equations that we do in math are actually not identities. So if you think about when we solve like 2x plus 5 equals 7, right? That's not an identity. It's not true for all values of x. It's only true for one value of x, and we're trying to actually find that value of x, correct? And so these ones are always true. So some examples of identities not having to do with trigonometry. If I said like 2x plus x plus 3 equals 3x plus 5 minus 2. Let me just double check my math here. So this actually is an identity. It is an equation, but if you simplify it, it says 3x plus 3 equals 3x plus 3. That's always going to be true, correct? Whether x is 0 or negative 5 or 1/2, that would always be true. Another example using factoring. If we did x squared minus 9 equals x plus 3 times x minus 3, that is also always true. That's an identity. Because it doesn't matter what x is, that's going to be true, no matter what. X could be 0 or negative 5 or 1/2. It would still be true. Okay? So that's what we're talking about today. We're not really trying to solve for x, okay? We're going to be simplifying stuff using identities, all right? So we're going to learn some basic identities here to start. And so let's get started here with our reciprocal identities. So for our reciprocal identities, the first three I think are going to be going to make sense to you. So cosecant of x is going to equal 1 over sine of x. And so that should be logical because we remember that cosecant is the reciprocal of sine, right? And then secant of x is going to equal 1 over cosine of x, which makes sense because secant is the reciprocal of cosine. And then cotangent of x can equal 1 over tangent of x because cotangent is the reciprocal of tangent, right? Awesome. All right, next up here, this one may take a little bit of explaining, but I think it will make sense if you kind of remember from our unit 6 that we did a couple of units ago. But here we have tan x equals, and this one's going to equal sine x over cosine x. All right, sine x over cosine x. Now to explain this one, you have to go back and think about the unit circle. So if you remember when we did the unit circle and we were looking for the trig functions on the unit circle, right? And we would look at the point at that angle and we would say the x value of the point was cosine, the y value of the point was sine, and to get tangent, you did y over x. Well, if sine is y and cosine is x and tan is y over x, then tan could also be written as sine over cosine because that's really just saying the same thing as y over x on the unit circle, okay? Got a lot of memes for this section, and so I'm going to sprinkle them throughout the lesson. So we'll get our first meme here that I think will actually help us remember this tangent identity right here. So let me show you that one. Here we go is our first meme. It's not even summer and I already have a tan. You can see that this person just wrote sine over cosine on their arm. And so now they have a tan on their arm. Get it? Ha ha. Okay. So this is especially apt today since it's nice and warm out. And so maybe we could start working on our tans. Okay. So just get some sine over cosine and then you'll have a tan. All right. Yeah, make sure we wear sunscreen though, right? Especially for white folks like me, because I gotta worry about your skin health here, okay? All right, so let's get back to the notes then. All right, so then we have another definition for cotan here, and this is actually also related to that, the unit circle. We actually used to do cotan was x over y. And so that one I would say would be then cosine over sine. So we actually have two identities for cotan here. And so some of you may be worried, you may be thinking, oh man, I don't know which, I'm not gonna know which cotan identity to use. Do I use one of them sometimes and one of them the other times? I got good news for you. You're gonna use the same cotan identity every time and I'll tell you which one, okay? So I'm gonna box up these four right here. So these four are the good four identities. So this last cotan identity, I'm gonna say that it's true, but not useful. True, but not useful, okay? So we're not really gonna use that one, but it's certainly true. It's like saying that Abraham Lincoln had a beard. It's like, yeah, that's 100% true and 100% not useful. Like knowing that Abraham Lincoln had a beard is irrelevant to your life. But it's true. That's like cotan equals 1 over tan. Same thing, okay? All right, next up, Pythagorean identity. This one's a good one. So this one says sine squared of x plus cosine squared of x always equals 1, okay? So I can actually show you this. I made this on Desmos here. So I put in here sine squared of pi over 4 plus cosine squared of pi over 4, and you can see the answer is 1. And even if I change this to pi over 5 now, the answer is still 1. You'll notice that when one of them is different, it doesn't equal 1. So like when I make that one a 7 and that one's still a 5, it's not 1. They have to be the same thing in both sides, in both trig functions. But if you do have sine squared of an angle plus cosine squared of that same angle, it's always going to equal 1, okay? So that is our Pythagorean identity there. For this reason, I always tell my wife, I say, you are my sine squared plus cosine squared and only, because she's my one and only. Oh man, that's so romantic. So next time you see Bay, tell them, you're my sine squared plus cosine squared and only. And if they understand analytic trigonometry, they're going to be very touched by that. And if they don't understand analytic trigonometry, they're going to be a little bit confused. But just explain the identity. It's okay. It's a pretty quick identity, so I feel like you can explain it. All right. Now, there are some modifications to this Pythagorean identity that are very popular, and so I'm going to write those down as well. And so the modifications come when I subtract one of these over to the other side. So if I subtract the cosine squared over to the other side, this would say sine squared of x equals 1 minus cosine squared of x. And so that is also true. And I'm going to say it's also going to be useful at times, that version of it, okay? If you kind of look at it, it's really the same identity. I just kind of moved something around, correct? So I haven't really changed it. And then the other one is just if I keep the cosine squared on the left-hand side and I subtract the sine squared over instead, that's going to be useful as well. So these are kind of the three versions of the Pythagorean identity that we're going to be using a lot of. For identities, remember they work both ways, right? So this one right here, for example, sine squared equals 1 minus cosine squared. That means if I see sine squared, I might want to change it into 1 minus cosine squared. But also, if I see 1 minus cosine squared, I might want to change it into sine squared. So they work in both directions, is my point. Okay, next up, we have our even odd identities. I'll tell you that these ones are probably the ones we use the least. I think I found one question on WebAssign for this section that has these, but it's still a good thing to know. So these have to do if you have a negative inside of your sine or cosine. So for a negative inside of a sine, you can actually move that negative out front and then turn it into a positive x on the inside. And technically, that's a more simple way to write it if we take the negative and move it out front, okay? So we are going to be doing that. Now, when we have a negative inside of a cosine, this one can actually just be written as cosine of x, and the negative just disappears. It's gone. It was magic. I can tell that some of you are doubting me on this, so I'm going to prove this one as well. So check this out. I did sine of pi over 6, and that's 0.5. Sine of negative pi over 6, that's negative 0.5. So that's as expected as we saw with our first identity for sine. When you have a negative on the inside, it turns the answer negative. But check this out. If I change this to cosine, cosine of a positive pi over 6 is 0.866. Cosine of a negative pi over 6 is the same exact answer. It doesn't turn negative, it stays positive. Okay? Well, what about tan? Let's check. So tan pi over 6 is that. Tan negative pi over 6 does turn negative. So that one is more like sine here. So we're going to move the negative out front of that one. So cosine is kind of the different one here. Cosine, when it has a negative in there, it just goes away. For sine and tan, when you have a negative inside, it moves out to the front, okay? I'm not even going to box those ones up because I feel like we don't use them enough. So these identities up here, we kind of have 7, right? Except these 3 are kind of all the same, just different versions. But these 7 identities are really what we're going to be using here, okay? All right, so we got a little meme for this because if you have all these identities, what do you have to worry about? Well, I would say you have to worry about identity theft. Get it? See, he's got the sine squared plus cosine squared equals 1 there, and he's trying to steal it. That's identity theft. Get it? It's funny. All right. Awesome. So let's start on some problems here, okay? But before we do, how are we going to do these problems? Well, our goal is to simplify. How are we going to simplify? Well, I kind of have a game plan that over the whatever 9 years I've been doing this, it's probably the best game plan and kind of takes you a step by step what we can do to these things, okay? So let's write this down over here. The first thing I'd always look for is change everything into sine and cosine. Necesitamos cambiar todos en el seno y coseno. Now, this actually takes me back to, remember when I told you like for cotangent, like we want to use this one and not that one, right? Do you see how that matches up with what we're talking about now, changing everything into sine and cosine? So if I have cotangent, I'd want to turn it into that one because that's turning everything into sine and cosine, whereas this one is not turning it into sine and cosine, all right? So that's first thing, change everything into sine and cosine. Second thing you can look for is Pythagorean identities. And I'm going to say on that one, only if something is squared, okay? We only use Pythagorean identity if something is squared. Remember what that formula said, right? Your sine squared plus cosine squared equals 1. In fact, we should probably write this up here because this is a common mistake. Is a modification that people make on the Pythagorean identity that's wrong is some people say that sine x plus cosine x equals 1 then, and that is not true. So cross off that equal sign. If they're not squared, it does not equal 1, okay? Sine x plus cosine x does not equal 1. Sine squared plus cosine squared equals 1. So we're going to use those Pythagorean identities if something is squared. All right. What's the third plan of attack? I'm going to say the third plan of attack is add or subtract fractions with common denominator, of course. I know I don't talk about common denominator a lot in this class. Just kidding. I talk about common denominator like all the time. Oh, I just thought of a meme. Hold on, verbal meme. Okay, I don't have time to make the, I'll make this later, okay? But I'll just tell you the idea right now, okay? Because I just thought of it, okay? So verbal meme, okay? So it's the galaxy brain meme, you know, where they go through the levels of like the brain, that format. Okay, so like the basic brain is like when you're in 4th grade and you do common denominator with numbers, right? So it's like 1/4 plus 1/2, and you do the common denominator. Okay, that's basic brain. Then like next level brain is in like algebra 1, you do common denominator with variables, right? So it's like x squared minus 9, and then x minus 3 is the other one. And you got to factor and do a common denominator. And then now we're galaxy brain is common denominator with words, with sine and cosine and stuff like that. It's like boom. All right. Verbal meme, y'all. Okay, good. All right. Next up, number 4. Number 4, which will be our last one, is my second favorite F word, factor. What's the first? You don't have to explain the joke, okay? It's going on in our heads. All right, cool. Second favorite F word. All right. My favorite is foil. All right, good. Function. Awesome. So that's game plan, okay? So let's go for it, all right? We're just gonna run down that list. The list is in order, okay? So let's start with number 1. You will not have to use all of these. All right, you'll start with number 1 and use as many as necessary. Usually only 1 or 2. Most of the time only 1, actually. So let's start off with number 1, okay? So number 1, can we change everything into sine and cosine? The answer is yes, right? So sine t, I cannot change to sine, so I'm going to keep that as sine because it's already sine. I'm going to put a little multiplying dot there. Secant of t, I can change to sine and cosine, right? So it's going to be 1/cosine of t. So in this case, these fractions are multiplying, right? So do we need a common denominator to multiply fractions? No. I can cross cancel if I can, but in this case, there's no cross canceling available. So I just do top times top goes up top, bottom times bottom goes on bottom. So we have sine t over cosine t. Now, remember our goal here is to simplify, correct? So have I simplified this problem? Is it simpler now from the original? I would actually argue yes, because the original was 2 different trig functions multiplying. Now it is kind of 1 fraction of trig functions. But I think I can simplify it a little bit further here. And so I will simplify it with 1 more step, which also answers the question, why don't mathematicians need to go to the beach? Because all you need is sine over cosine to get a tan. So I would state my final answer there as tan t, which once again, I would argue is a lot simpler than the original question, right? And our goal again here is to simplify. We're not figuring out what the variable is, we're just simplifying the expression. So I have done that. I have simplified this, okay? All right, so let's move on to number 2. So number 2, can we change everything? Can we change everything into sine and cosine? I would say we can change one thing into sine and cosine, right? So I'm going to keep this as sine x. I'll put it over 1. We'll do this one as cosine x. We'll do this one as 1/cosine of x. Once again, these are all multiplying, so we don't need to worry about common denominator. We are actually allowed to cross cancel, and we do have some cosines there that we can cross cancel. So what's left is really just my favorite brand of nasal decongestant, sin x. That was a joke. Quick warning here for WebAssign. So you'll notice that like this one, they use the variable t, that one, they use the variable x. Actually, if we were all here on campus and I was grading like a piece of paper that you're writing on, if you put the wrong variable on there, I would actually not mark that wrong because I actually don't even really care what the variable is. But if WebAssign is grading your thing, they do care about which variable you put in there. So just be careful about if they usually use x, but if they put t or y or n in there, you do have to kind of display that in your answer, right? You have to keep that the same in your answer, okay? All right, let's move on to number 3 then. So number 3, we have secant of x over cosecant of negative x. Now, the first thing I notice here is we have the negative inside of the cosecant. Now, we didn't really have a rule for negative inside of a cosecant. So I'm just going to switch everything to sine and cosine and kind of see what happens here. So we have 1 over cosine x over 1 over sine of negative x. So you'll notice then, when I change the cosecant into 1 over sine, whatever was inside the cosecant is now inside the sine. So if it was a negative inside there, it's now a negative still, okay? Well, now that it's a negative inside of a sine, we have a rule for that, correct? We said if we have a negative inside of a sine, we can turn that positive, but we have to throw a negative out front of it, yes? So now I'm gonna multiply by the reciprocal here. So times negative sine x over 1. Whenever you have a fraction over a fraction, we multiply by the reciprocal, correct? All right. Once again, multiplying fractions, we do not need the common denominator. We can cross cancel usually or sometimes, but not in this case. And so we are left with negative sine x over cosine x. Top times top up top, bottom times bottom on bottom. And then just like number 1, we can simplify this one more step. When you have sine over cosine, a more simple way to write that is tangent. So this one, since we have a negative, that has to kind of come along with it. So we'll have negative tangent. This one again would be negative tangent of x, because that was the variable we started with, okay? Or as I call it, the variable. Boom. My name's Barry. All right. All right, number 4 is a lot like number 3. So if you'd like to kind of jump ahead here and try number 4 on your own, I'll go ahead and wait 10 seconds and then I'll go for it. All right, so this one we're going to go sine x over cosine x over 1 over cosine of negative x. So this time we have a negative inside of a cosine. So our rule for that one was that the negative inside of the cosine can just magically go away. So I'm just going to change that to a positive x. I'm going to go ahead and multiply by the reciprocal there. So times cosine x over 1. Cross cancel. And all we have left is sine x over 1, which I would just write as sine x. All right. All right, nice and easy on those first 4, right? Now is where it gets hard. Number 5. I actually really like number 5. There's 2 ways to do number 5, so I'm going to do one underneath here. I'm actually going to do the other way over here because I think they're both really good ways to do it, and they end up at the same answer. So I mean, they're both correct. So let's kind of go down our list here. So number one, change everything to sine and cosine. No can do on number 5, right? Everything is literally all sines and cosines, yes? Number 2, Pythagorean identity if squared. I do have some squared stuff here, correct? So this is the technique I'm going to use first, because if I'm following my list, I should use a Pythagorean identity here, okay? But we're going to use kind of a Pythagorean identity a little bit of a different way. So this right here, sine squared times cosine squared, that's not 1, right? 1 is sine squared plus cosine squared. So this is not 1. But what I want to do actually on this one, I actually want to get rid of the sine squared, because if you'll notice that kind of like sticks out here. It's like everything else is cosine and that one is sine, right? So let's get rid of that. So what can we turn sine squared into? Well, go back up to our Pythagorean identity. And if we look at this first modification over here, it says we can turn sine squared into 1 minus cosine squared. So I'm going to go ahead and do that and see what happens here. So I'm going to turn this into 1 minus cosine squared, and I'm going to keep everything else the same. So now you can see I have everything written in terms of cosine. What would I do next? Well, I see this cosine squared out here that's multiplying by a parentheses. So I would go ahead and distribute that in there. So cosine squared times 1, obviously cosine squared. Cosine squared times cosine squared will be cosine to the 4th, but it's negative. And then I'll keep this cosine to the 4th out here. Now I have one more step and I'm done. And it's actually, I think, a super easy step. Combine like terms, right? What's cosine to the 4th minus cosine to the 4th? It's 0. They cancel out, right? So all I'm left with is cosine squared x. I'm done. Technically, I could change that cosine squared x into 1 minus sine squared x, but I think that would not be simplifying, right? That would be complicating. And I'm trying to simplify. So cosine squared, I would say, is the simplest way to write that. Okay. So that's the first method. If we kind of follow our list strictly here, we would use the Pythagorean identity, okay? Now, the other way to do this is actually using the fourth plan of attack on our list, which is factor. So when you factor this, you got to see this as 2 terms. 1, 2. And what we're going to do is out of those 2 terms, the type of factoring we're going to do is GCF. We're going to take out a common factor. So what do those 2 terms have in common? I would say they have in common a cosine squared x, right? So if I take the cosine squared x out front, cosine to the 4th is going to turn into cosine squared. And then sine squared cosine squared is just going to turn into sine squared. If you're not really seeing that step, try this for me. Try distributing this cosine squared back in. Look at this. Cosine squared times cosine squared is going to give me that cosine to the 4th. Cosine squared times sine squared is going to give me this sine squared cosine squared term. Okay. So how does that help? Well, look on the inside of that parentheses. Cosine squared plus sine squared. Isn't that 1? It is. We wrote it as sine squared plus cosine squared, but the order on addition doesn't really matter, correct? So that is still equal to 1. And then cosine squared times 1 would just be cosine squared of x, obviously. And we end up at the same spot. Should you do these 2 different ways if possible? I would actually say no. I'm not trying to double your work here. I just did that because we're doing notes. So I want to show you kind of that there are, on some cases, different ways to do it. And I also want to show you what does factoring look like in these. And so that's why I did it in the orange, okay? We had cosine squared plus sine squared there turned into 1. So how about we look at another meme? Sounds like a good idea, right? So here's a good meme. All right, so creepy guy from Big Bang Theory says, I wish I were sine squared and you were cosine squared so that together we could be 1, all right? I guess that's kind of derivative of what my phrase I told my wife, you're my sine squared plus cosine squared and only, but that's all right. This one I found on the internet. The other one I came up with on my own. So it's not the exact same joke, just related. Okay. All right, let's get back to the notes. Let's take a look at number 6. And we still have one more meme upcoming, so we'll look forward to that at the end of the class period. So for number 6, I see right away that there's a tan squared there, so I'm gonna use my first plan of attack, which was change everything into sines and cosines, correct? So we're gonna go cosine squared x plus cosine squared x times, and then this one I'm gonna change into sine squared x over cosine squared x. And so please notice there that when the tangent was squared, when I'm changing it into sine over cosine, it's turning into sine squared over cosine squared. Both of them are now squared, okay? Well, PEMDAS says I should multiply those fractions together before adding. So multiplying those fractions, I do not need common denominator. I am allowed to cross cancel, which you can see we have a nice cross cancel there, full on cross cancel. So we have cosine squared x plus sine squared x. And wouldn't you know it, there it is again, our favorite Pythagorean identity, sine squared x plus cosine squared x equals 1. So the answer to all that mess is 1. Crazy. So that means if I went back on Desmos and I wrote all this, but I put an angle, I put pi over 3 in for every x, it would just tell me the answer is 1. And if I change the angle, it would come out to 1 again. It's crazy. All right. Let's go on to the next page then, and we'll do, I think we only have time for one more. So we'll do number 7 today, and then next week we'll do numbers 8, 10, and 11, but we're not doing number 9, okay? So don't even think about doing number 9 because we're not doing it. Got it? Okay, wait a minute. There is no number 9. Okay, that's why we're not doing it. I forgot. You guys know what happened in number 9? 7, 8, 9, of course. Get it? All right, cool. No, actually, I just messed up the numbering and forgot. I took out, there used to be a number 9 and I took it out. Actually, I took it out so I could say that joke. All right, cool. So let's go to number 7. So number 7 looks like a lot of stuff that we can change to sines and cosines. So I'm going to start off with that. So we're going to go 1 over cosine of x minus cosine x over 1 over sine x over cosine x. So that's kind of my first plan of attack there, is change everything to sines and cosines. Now, this actually doesn't look more simple. It actually looks more complicated right now, but worry not. We're gonna make it more simple in a minute. Nothing is squared, so I cannot use my Pythagorean identity, but I have some fractions subtracting on top, so I can do a common denominator subtraction up there, right? So I'm gonna go ahead and make my common denominator. I gotta multiply this one by cosine x over cosine x. So then I'm going to have the common denominator of cosine x here. And then in my numerator, I'm going to have 1 minus cosine squared x. Now, 1 minus cosine squared x, this actually seems familiar to me. If we think back to our Pythagorean identity, we said that 1 minus cosine squared x can be turned into sine squared x, right? We actually use this identity the other way on number 5. On number 5, we turned sine squared into 1 minus cosine squared. Now we're going the other way with it. So I'm going to change that 1 minus cosine squared into sine squared over cosine x over sine x over cosine x. All right, now I'm going to multiply by the reciprocal here. So times cosine x over 1. Nope, times cosine x over sine x, excuse me. And now I'm going to do some cross canceling. Cosine cancels out with cosine. Can I cancel out sine squared with sine x? Partially, right? Sine squared is really sine times sine. So I can cancel out like one of those sines with the sine x on bottom. So I am left with just that last sine x on top. Everything else got canceled out, okay? Pretty sweet that we could, this is like, you can really see the simplification, right? Especially from our first step all the way down, all of that just turned into sine x. Pretty awesome if you ask me. All right. Good. Yeah, I love these. Sometimes I do these and I'm like, I go down one path and then it like doesn't work, especially on the more difficult ones. I have to go like go all the way back to the beginning and then try something else. Some people get very frustrated by that. I think it's like fun. I think it's like a game or a puzzle. But you know, I do this for a living, so I get it. All right, our last meme of the day. It's a good one. Here we go. We got sine gerene over cosine gerene. And whenever I show this meme, someone always will say, what is that, an orange? And I'm like, yeah, sine gerene over cosine gerene equals orange. Yeah, no, you got it. Perfect. All right. No, it's a tangerine, of course. Tangerine. Okay, cool. Awesome. Good meme day.